Okay. I think we're set right now. Okay. Let's take a look at what we need to get done for today. So let's do a recap of yesterday's stream. So we actually created a new struct for memory. So we created an array of around like 65 kilobytes. And we created functions for these functions, reading byte, half word, and then writing each one separately. And that would be up here under this. So yeah, right here. So like, where's the, oh yeah, okay, right. Yeah, so read bytes, so we have the address and then we access the memory address for each one. So like for a byte, we just need the 1 byte of memory address, and then this we need, for half word we need 2, and for word we need 4 bytes of memory address, and then we do the same thing with writing, just we take a value and then put it into the address. So yeah, that's what we did yesterday. So today we are going to be continuing off writing more of the instructions, and why we did that yesterday was because we needed to do the load byte unsigned, load half word, and all the instructions for that, for loading these values, which in the risc-v instruction set here we have for the load, for the memory instructions for loading bytes, loading half words, and loading words. Like, this is the equation, so we have to access the memory for the value of rs1 and adding it to the immediate. So, and then putting in the destination register. So that's what it was for this. So now it's a bit different with a store byte. So we have to do S type today. We did branch type yesterday as well, and also we did all the control instructions. So we did jalr, jump and link register. We did all the branches. So today, what we have left to do, so we have all the arithmetic done from 2 days ago. Memory, we did half of it, so we need to do S types. This is all done, and then we need to do U type, and then the environment calls. We need to see how to do those environment break and environment call. So yeah, actually it's not, we're pretty close. We're pretty close to finishing this part of it, and then we'll move on to the next part. So yeah, let's just continue writing. So for the S type, we have, okay, so we need to store a byte, store a half word, and store a word. Okay, so the format is we're accessing the memory of the value of source register 1, adding it to the immediate value, and storing that into the register source 2. Or wait, is it the other way around? Okay, so for this one, we added the value and loaded it in, so. This one we're storing it here. Okay, let's just start writing. I kind of forgot. Let's take a look at I need to take a look at the instructions. Store byte. Call SB. Stores 8-bit value from low bits of register RS2 to memory. Okay. Right, okay. Just get code ready to start. So store by. Okay. Yeah. So for this case, think I kind of understand it. So okay, let's do it. So for writing our case for SV, starting byte. So what parameters do we need? So we need the address, right? And the address is gonna be so the address is gonna be taking the memory value from register 1, right? So we're taking that value and then we're adding that to it. So basically the same as this part, but now we're putting it into address. And so now we needed the rs2 value, so we're gonna do value and what do we need? Just the register number. We don't need the read word, so we just need to have read register for rs2. So it would just be like address value. Pretty sure, right? Well, it wouldn't be writing a register, we'd be writing, so we'd be writing byte, right? So mem dot write byte, I think. Let's take a look. Is it not the memory of it though? Okay, so memory at address, space the address is okay, we're just getting the address, we're not getting the memory at the address. Right, okay. Let me see if I can figure it out without looking at it. So, okay. It's because we needed the memory from this address. Like adding this together with the address, the memory from that, and then storing it into, loading it into that value. But this is storing it. Storing the value from rs2 into the memory, so like you don't need to actually grab the memory address, you just need the address. You don't need to grab the memory from it. So okay, let's see. That was probably the worst explanation, but let's see. Data moves from memory to register. You need to read from memory to get the value. And that read word address fetches the value stored at that address. Then you write the value into a register. So data moves from a register into memory. You already have the value in the register via. Okay. Oh, we already have the value. Okay. You just need to write to the correct address. I see. Okay, wait. So, because there's no way to actually get the value of, like, the value of rs1 plus the immediate without calling that memory function, reading the memory, you won't actually be able to get it. That's why we do that. But in this case, we already have the value that we're storing it into. We already have the value from the register, we're just storing it into memory now. So we don't need to actually access anything. We need to write it to memory. Okay, I understand. I get it. Let's write it to memory. So in the case of that, I understand. I think we can do the same with these. So for storing half word, should be the same thing, but for the case of this, okay, so we're still reading from that register, but we need to grab a different value for the immediate, right? Or would it just be the same? I think it would be a different value, I think. Let's see, I think we need to offset. You don't need to do any bit of manipulation here. Right, half word already handles that. Okay. Wait, let's take a look. Wait. Oh, right, our function. Yeah, function should already handle that. All that. I totally forgot. Just handle all the addressing by itself. Yeah. Yeah, we don't need to do any more like that. So you just need to change the function. It should be the same for the last case too. Storing a word, we just need to make the function like that. So I think that's the end of the S-type instructions. Okay. So now we have the last, so now we have arithmetic done, memory is all done, controls done, finally just the last couple in other instructions for the 32-bit version of it. So add upper immediate to BC, alright, so let's just get the case started. Alright. Oh, well, I'm wrong here. Right. Oh, I copied too much, that's why, my bad. I didn't realize. Okay, so add upper mediate to the PC, okay? I'm just gonna get rid of this. So, for the case of this, taking the program counter and adding it to the immediate, shifted by a certain value, and storing a destination register. That's not too bad. So let's do that. Oh shoot, program's about to find my bad. Okay. So for the first value here, we need our destination register, and then we'll add a variable here. I'll just call it like into T. I'll just call it upper immediate. Alright, so what it is our program counter variable added by the immediate and left shifted by 12 for that. And we're not writing here, we're just reading the register. So it'd be right reg. So it should be that, and change to upper immediate, and then this case, which is LUI load upper immediate. So now for loading upper immediate, no program counter needed since we're just loading the value and we're not adding anything. So we're just loading in the upper immediate, which is just literally just this, but I should probably copy it for this, it's easier since everything is already there. Just taking off this value. Should be good here. And we can write the final two cases. Well, these are kind of interesting. There's not really any arithmetic, so what does it actually do again? Just turn control to a debugging environment, and the other one was recall. Oh, it's right up here. Used to make a service request to the execution environment. The EI will define how parameters for the service request are passed, but usually these will be defined in defined locations in the integer register file. Okay, I don't know how to handle those cases, but we'll just get these cases in first. Oh, yeah, I keep forgetting. We already wrote the logic for the shift. We don't need the shift. This would just be that. Okay. System level instructions that enable CPU trigger trapping into the operating system or debugger. Yeah. For now, our emulator doesn't have a OS or trap handler, so you have a few options. Just print a message indicating the instruction was hit and halt execution. So the flag and core, the fetch, decode, execute, check. Ignore them for now within the case. Option 2 is the cleanest long term. I need to know more about these calls. Can you explain me more about the e-call and the e-call to understand why to implement? into the screen, read a file or allocate memory. You can do it directly instead of sets up some arguments and registers and fires the call, which hands control to the OS kernel. Kernel looks at the arguments, does the work, and returns control to the program. So I need to do something for me. It's a debugger instruction. When I hit, it's supposed to hand control to a debugger, so you can inspect the program state. Registers memory PC, except program counter, etc. Okay. Yeah, that makes sense. Okay. Okay, I think I have enough context to kind of see. So, in our core struct, just setting up a bool for that. Right. And then when we hit the cases, we just call it which one is first. You break. Doesn't really matter, but I'm just gonna do it like that. Follow the order. Okay. So we need none of that. We're just setting our halt to true. Lowercase in C++ forgot. Then case of call. I guess same thing. I guess that's what Cloud kind of wants me to do. I'll call it halted because that's what it said. I guess we can check. But if this is fine for now, if like we can just have this, then we're done with that part, and we'll see how we have to continue. C++ memory variables aren't automatically initialized unless you specify. Okay. I actually didn't know that. So just default initialize it to that list initialize it to false. Yeah. Okay. Unknown case. And ideally just print out like just print out like unknown instruction. That's kind of the only thing I can really think about. I don't think this is that serious, but causes a fault, halts execution. In real CPU causes pause execution. Continue to run after hitting an unknown execution computer score. Okay. Tells you exactly where things go wrong. Oh yeah, so we have like the exact place where it went wrong. So the program counter would be nice to have. That's true. While loop. So I guess we can put it in the header file. And then execute it. That makes sense. So while it's not halted, and then we just run the function, right? I'd assume. Whoa. We have to fetch it first, so. So we'd have to call like the decode instruction variable. Fetch the CPU, but the CPU reads the next instruction from memory that are stored in PC. That means reading 4 bytes from memory at address. Okay. Got it. I don't know why I'm not understanding this right now. Today's stream has been pretty bad, not gonna lie. I've been relying too much on Claude today. Okay, this is the program counter. So wait, the program counter just adds 4 each time each instruction that's added on. It'll just keep doing that in a loop, I guess. Calling her, what's our function name called? Decode instruction. It takes a value, so what value would we take in? We take in the raw instruction, because that's what we're reading the memory from. So we're taking 4 bytes at a time, and then that'll be our instruction. So that there. It's a fetch. Now we need to execute it. Fetch, decode, execute. So now we need to execute, which will be our execute function. It is called execute. Oh, he is called. Not gonna lie, we're not having a good stream, bro. I'm understanding, but at the same time, I'm not writing it I can't get it from scratch for some of these right now. I don't know, it's just not running through it now. Might be a bad day today, I don't know. I'm guessing you delete that so it doesn't run. I need to take it one step at a time, bro. Just we need to chill out and just do one step at a time. I need to read this again, bro. Okay. So I understand this stuff, all this stuff. Here's where I need to understand like what's going on. Okay, so we had our fetch, decode, and execute. We already wrote the decode. The decode is already all like the logic in there. The same for the fetch and execute. We just need to get it in now. So our fetch. Okay, so well, it's not halted, right? So if we got the equal, like halted equals true, these three, it would just break out of this loop. So you have the loop running. Alright, for the raw instruction. Okay, so we're taking the memory address, and we're reading 4 bytes of memory address at a time because the program counter moves in 4 bytes at a time. From what I remember, from what I recall. So let's go back up. Let's go back here. Okay. Reading a word. Xing the first byte. No, the first, the first byte, second byte, third byte, fourth byte. Starting from the least significant byte address, moving up to the most significant byte, because this is little endian, so as the address increases, we move to more significant bytes, higher bytes, so that makes sense. So we're basically building our 32-bit instruction from that, and we're reading it. And our program counter moves up as we do the instructions. But now we need to decode the instruction. So we have the decode instruction that I get, like the raw instruction, okay? And then we need to execute it, which is finally like the memory address and the instruction where we're being placed at, which makes sense to me. I understand. I think I got it. I was just feeling a bit weird because I couldn't write it from my own brain, but it's fine. It happens once in a while. Okay, let's try and get it. So we can still have this. But we should also have our other mode, and we should be able to choose from those modes. First, let's just do the outline for this. Creating memory object, so So remember, so we just need the memory and set that equal to we can just do it like this. We don't need to actually, right? Include interpreter.h. Okay, now it actually understands. Now we also need core. Execute what do you exactly, just the mem. But wait, what? I thought we need 2 arguments for that. Oh no, that's for run. Okay. Okay, a rocky stream so far. I guess we can try. Okay, wait, so which function should we be referencing? So to be writing a word, right? Writing a word, which takes the I'll call it mem, since we have it before. Mem.write word, and the parameters for that would be the address and the value, right? So we can start at a 0 address, and how would we get a value in? So for getting a value, we need to call our convert binary function. Right? Okay, so we have get binary, and we need to convert binary on assume something like that. I feel like something like that. I just need to, let's just check if this would be a good way of doing it, of handling it. One instruction, loading a single instruction at address 0. Real program needs multiple instructions. How would you load several? And which the last instruction means the program actually halts quickly. I already wrote code out run. Okay, so one instruction, so to load multiple instructions. I would like probably call this multiple times, like set 4 different variables for it, because we can't do this, because then it might go in an unspecified order, so we don't want that. So we probably just make 4 different variables calling to that and convert all of them. That's, I guess we can give that a try. So I'm just gonna take this for now. So, okay. Get binary returns a string, so we need to have a couple of string variables. One second. Go back to our decoder. It only takes in 1, so we can't put multiple instructions in. So this probably wouldn't work either. So what else can you do? Dude, it's like I have some sort of like writer's block or something right now, dude. I can't think of what's to actually implement. Yep. I'm actually stuck here, dude. Alright, so single instruction. How do you load several? It doesn't make any sense though. Like I don't. multiple instructions. Alright, let's just ask God. Because I actually have no idea. Instruction 1 under 04A. Would it take in user input like I guess we can hard code values. So we'd have to take a stream. Let's just do. So what did it say we can do? Putting the value 5 into x1, so that's. Yeah, so that would be the instruction. So the immediate of 5. But from what other register are we taking it from? Alright, let's just get the bit strings for these. Let's just do the bit strings for these. I'm just gonna have to do the bit strings. So we'll hard encode these values in. Did I not copy it, bro? Low-key, after this part, we're probably gonna end the stream low-key. Because today was not really the best stream. I was having a lot of trouble with this part, so probably pick it up after tomorrow after I read up on some more stuff. We're gonna have to change. And lastly, 12. Okay. So we have hard-coded values in now. Oh yeah, I think that's gonna be it for today. Just for now, we'll pick up tomorrow. I need to like refresh on this topic a bit more because I was actually struggling today. So we didn't struggle on any of the other streams, so on the 7th stream we struggled. That's okay though. That's all good. We'll just pick up tomorrow.